So now we're ready to start looking at some of the reactions that we can do on the alpha carbons of our aldehydes and ketones and other carbonyl compounds. And we're going to start by looking at the reactions that will halogenate at the alpha position. So these are going to be alpha halogenations. And there are 4 of them that we're going to look at. First one that we're going to look at is acid-catalyzed alpha halogenation. This reaction we can do with an aldehyde or a ketone. I'm going to draw an asymmetrical ketone. And this reaction can be done with pretty much any one of our halogens, bromine, chlorine, or iodine, acid catalyzed. So I'm putting H plus in square brackets under the arrow because it's catalyzed. And it is going to replace one of the alpha hydrogens with the halogen, bromine in this particular case. And this, because this is an asymmetrical, I chose to draw an asymmetrical ketone. We've got 2 possible products, or it could replace either alpha hydrogen on the left side or alpha hydrogen on the right side, and we find that the major product is the product that has the bromine on the most substituted alpha carbon. Most substituted of the 2 alpha carbons. But we do make both products, so this is our minor product. And we could do this reaction easily with chlorine or with iodine. So it's a great way to stick a good leaving group on a molecule if that's what you would like to do. Let's draw the mechanism for this reaction, because the mechanism is pretty simple. We're going to use the same ketone again. Actually, I'm turning it around. And this, because this is an acid catalyzed reaction, the very first thing that's going to happen is protonation of the oxygen with the acid. So our first intermediate looks like this, with the hydrogen on the oxygen and a full positive charge on the oxygen. And then we're going to draw in a couple of alpha hydrogens so that we can work with them. The next thing that happens is water, which is left over from the first step. Water is going to deprotonate at any one of the alpha hydrogen, and it is going to show a preference for an alpha hydrogen on a more substituted carbon. So that's going to give us carbon-hydrogen bonding electrons coming in to make a carbon-carbon double bond, the carbon-oxygen double bond moving up to a single bond, just like that. This, what we've made right here, is the reason why it shows preference for the most substituted carbon. If it was pulling from the other side of the molecule, you'd be making a less substituted, less favorable alkene. It still happens, it's just not the major product. So we've got this guy, which is an enol, and the enol lone pair of electrons on the oxygen are going to come right back down and allow those carbon-carbon electrons to reach out and attack our halogen. I'm going to draw it with bromine. This is going to break the Br-Br bond. And so now we have positive charge back up on the oxygen again. We have added the bromine to the molecule, to the alpha carbon, And all that we have left to do is one last deprotonation. And we have regenerated our acid catalyst, and we have halogenated our ketone. Now, one of the nice things about this particular reaction is that the product can be easily converted to a conjugated diene or alkene. The product of this reaction right here can be converted to a conjugated system in this particular system. We're going to have a carbon-oxygen double bond conjugated with a carbon-carbon double bond. So let's take a look at how that would happen. And we're going to use the same product, this guy right here. We're just going to keep reacting it. So to do this, we just need a good base. This is just going to do a standard elimination reaction. The base is just going to be grabbing any one of the hydrogens out here, moving the carbon-hydrogen electrons in to make a double bond and getting rid of that leaving group. So this makes a nice conjugated molecule. And the bases that are good for this reaction would be like what we would expect our bulky base. It's a great base for doing a reaction like this because we don't have to worry about it trying to do anything else. We can also accomplish this with lithium carbonate, Li2CO3. So this is a weak base, which means it's not going to try to do anything else. And also pyridine, which is a very weak base. So any one of those three you would see as being used to convert this to the alkene.